Welcome, listener, to another deep dive. Today, we're plunging into a really interesting corner of the online encyclopedia of integer sequences. It's OEIS, OE000298.
Yes, O000298. The title is Number of Partitions into Non-Integral Powers.
Non-integral powers. Okay, that already sounds intriguing.
It is. What's fascinating here is how it sort of stretches the whole concept of partitions. Usually we think partitions, we think sums of integers.
Right, like partitioning 5 into 3 plus 2 or 1 plus 1 plus 3 and so on.
Exactly. But this sequence, it looks at sums involving non-integral powers, specifically square roots. It's this really compelling intersection of number theory and, well, other areas, as it turns out.
Okay, let's unpack this definition then. The sequence, AN, it represents the number of solutions to an inequality.
That's right. You're looking for sets of positive integers, let's call them ISA, where the sum of their square roots, so I112 plus by 212, and so on.
That sum has to be less than or equal to n.
Precisely. And there's a condition. The EC values themselves, the integers under the square root, have to be positive, and they're ordered. So 1 or by 1, or by 2, or that just avoids counting permutations of the same set.
Oh, okay. So squirt 1 plus squirt 2 is the same combination as squirt 2 plus squirt 1. Got it.
Right. And this definition, it allows for a much, much broader set of partitions than the standard integer ones. For example, A1 is just 1.
Makes sense. Only square root 1 here.
Then A2 is 4, but then for N3, the value A3 jumps to 12.
Wow. Okay. 1 to 4 is one thing, but 4 to 12, that's quite a leap. What are some of those 12 solutions for N3? Can you give us a feel for them?
Yeah, it's a good illustration. You get the single terms first, like squirt 1 is 1, that's E3. Squirt 2 is about 1.414, also A3, all the way up to squirt 9, which is exactly 3.
Okay, so that's squirt 1 through squirt 9. That's 9 solutions already.
Correct, but then you have sums like squirt 1 plus squirt 1, which is 2. That works. 1 plus squirt 1 plus squirt 2. That's roughly 1 plus 1.41, so 2.414, still less than 3. Then 1 plus squirt 3 is about 2.732, also works. And squirt 1 plus squirt 4 is 1 plus 2, which is exactly 3. That counts too.
Ah, I see. So those are the other 3, making 12. It gets complicated fast with those irrational numbers.
It really does. It becomes quite a non-trivial counting problem very quickly.
So this isn't just some, modern mathematical game. You mentioned it has a history.
Oh, absolutely. It's got a solid pedigree. The sequence, it has the keyword non in the OEIS, meaning the terms are non-negative. It was notably included way back in N.J.A. Sloan's 1973 Handbook of Integer Sequences.
The original handbook?
The very one. And then again in the 1995 encyclopedia. But its roots go back even further. There's a 1951 paper by B.K. Agarwala and F.C. Alok.
1951. Wow. What was the title?
It was titled Statistical Mechanics and Partitions into Non-Integral Powers of Integers.
Okay, hold on. Statistical mechanics. That's where this gets really interesting. How does this concept, summing square roots, connect to physics?
Right. It's a fantastic connection. So in statistical mechanics, you're often modeling systems like gases or particles that can occupy different energy states.
Usually pictured as discrete steps, like energy levels 1, 2, 3.
Exactly. Simple models often assume integer energy levels. But Agarwala and Alok considered, well, what if the energy states or the quanta aren't simple integers? What if they relate to, say, square roots or maybe other fractional powers?
So the energy isn't just E, 2E, 3E, but maybe squirt 1E, squirt 2E, squirt 3E, something like that?
Sort of, yes. They realized that partitions like our E000298 sequence could actually model the distribution of energy or perhaps other properties in systems where the underlying physics, maybe quantum effects or degrees of freedom, don't fit neatly into integer boxes. It allowed for more nuanced models moving beyond, say, the ideal gas law to describe more complex physical realities.
That's really profound, taking this abstract number theory idea and finding it mirrored in the physical world.
It truly is. It shows how mathematics can be this underlying language.
It really underscores that point. Okay, so we've had a concise deep dive into OEIS sequence A000298. We've seen its unusual definition, worked through an example, and traced its history right back to this surprising link with statistical mechanics.
In thinking bigger picture, the fact that this specific type of partition involving non-integral powers actually found a use in physics.
It really makes you wonder, doesn't it? It suggests that maybe many abstract mathematical ideas are just sort of waiting for us to find their physical application.
It definitely poses a question for anyone studying number theory or physics.
What other sequences, what other abstract structures tucked away in places like the OEIS might be secretly describing parts of our universe we haven't quite figured out yet?
A really great question. And here's maybe a final thought for you, the listener, to ponder. How might this sequence, A000298, change if we weren't summing square roots? What if it was cube roots? Or, some other fractional exponent? What kind of complexities or maybe even new connections would emerge then? An excellent question. It really highlights the endless territory still left to explore in mathematics and its connections to everything else.